Hey up guys, welcome back to part 2 of binary representation and compression. Last week what we did was we did numbers to binary, binary to hexadecimal, hexadecimal to denary and decimal. And we've got all of that binary stuff out of the way, so we don't really need to touch it again. I've just got a little start for you today and we'll work on getting you a test. But today what we're going to be doing is we're going to be doing something brand new, which is logic gates, and I'm going to go into depth into that in a bit. But for now, what I'd like you to do is I'd like you to answer these questions. Firstly, I'd like you to pause this video and convert 81 into binary, 79 into hexadecimal, and AA into decimal. So decimal's denary. Okay, so pause the video, then we'll go through the answers. Okay, guys, welcome back. Hope you found that all right. So let's go through answer number 1. So first up, we need to convert 81 into binary. Well, 128 is bigger than 81, so we don't need it. 64 is less than 81, so we're going to take it. 64 plus 32 is 96. 96 is bigger than 81, so therefore we're not going to take it. 64 plus 16 is 80, so that's less than 81, we're going to take it. And then it's literally just a case of adding 1 on. There we go. So now we've made 16 plus 64 is 80, plus 1 makes 81. Okay, so 79 into hexadecimal. First up, we need to convert it into binary. So 128 is bigger than 79, so that's a no. 64 is less than 79, I'm going to take it. 64 plus 32 is 96, therefore I don't need it, so it's a 0. 64 plus 16 is 80, that's bigger than 79, so I don't need it. 64 plus 8 makes 72, therefore I'm going to take it because it's less than 79. 72 plus 4 makes 76, so I'm going to take it. 76 plus 2 is 78, that's still less than 79, so I'm going to take it. 78 plus 1 makes 79. Okay, so let's just copy down our 2 numbers because we're breaking it in half. So we've got 4 ones this side, 1, 2, 3, 4. And this side we've got 0, 0, 1, 0. Now we need to change the columns, change, don't they? So 8, 4, 2, 1. 8, 4, 2, 1. Okay, so this here is 15. And this here is 4. So we've got 4, and what's 15 in hexadecimal? A equals 10. And if A equals 10, therefore B equals 11, C equals 12, D equals 13, E equals 14, F equals 15. Then we glue it together and we have made 4F. So let's check our answer. 4 times 16 is 64. Plus 15 makes 79. Therefore, we must be correct. Okay, so this next one is you can work backwards. So if we've got AA, we cut it in half. So we've got A this side, A this side. What does A equal? 10. 10. Now we make 2 4-bit numbers, 8, 4, 2, 1. 8, 4, 2, 1, and we make 10. So that is 8 and 2. And then we glue it together. So we have 1, 0, 1, 0, 1, 0, 1, 0. And then we just need to do our binary columns and convert it into decimal or denary. 28, 64, 32, 16, 8, 4, 2, 1. Okay, so 128 plus 32 makes 160, plus 8 makes 168, plus 2 makes 170. So let's double check our answer here. So 10 times 16 is 160, plus 10 makes 170. Perfect, we're correct. Okay, guys, so that's all of the binary stuff done and out the way. Today, what we're going to be doing is we're going to be doing logic gates. Okay, so these logic gates basically represent binary in a computer. a computer is made up of millions upon millions upon millions upon millions upon millions of transistors. And so these transistors let power in, and if it lets power through, it's a 1. They're like gates. And if it's power's not flowing through, it's a 0. Now, in order to have some logic in a computer instead of just this power running here, there, and everywhere randomly, we have what's called logic gates. Now, these logic gates basically let power through based on a condition. So, for example, like this OR gate, if anything is on, then the output is on. So what that means is if you've got any bit of power on both legs running through, power will be output the other side. So we have, let's come back, I'll show you a truth table. We have what's called a truth table to represent this. So I'm going to draw the logic gate firstly. So an OR gate looks like this. Right, so it's got like fins on the end. That's how I remember it. And we have what's called a truth table. So a 0 represents off, and a 1 represents on. If anything's on, it's coming on outside this side. So, for instance, if we have on that leg 0, 0. So if we have 0 here and 0 here, what's going to be output this side? Okay, so if A was 0 and B was 0, what would Y be? Well, if anything is on, therefore it's on. So nothing's on here. So the answer is 0. So if A was 0, B was 0, Y would be 0. Okay, so let's have a look, see if A was 0 and B was 1. So what we do is we'll rub out the 0, 0 now, and B is now turned to 1. So we have a 1 going through this now. So something is on, B is on. So therefore Y is 1 because B was on. If anything is on, therefore it's on. All right, the next one is A is 1 and B is 0. So let's get my rubber. Rub it out. So A is 1, B is 0. So if anything is on, therefore it's on. So what's Y? The answer is 1 because A is on. Now, next up, we have 1, 1. So if anything is on, therefore it's on. I think you've already guessed it by now, but Y is 1. Because A and B are both on this time. This, guys, is called an OR gate. So OR. And so basically, if anything's on, it's on. Here on this right, what we've made is we've made a truth table because this is every single combination you can possibly have for A and B. How I remember it when you're drawing out a truth table is 2, 1. So you start off with 2 zeros, 1, 2, and then 2 1s. And then 1. So 1, 0, 1, 1. 1, 0, 1, 1. And you've made your truth table. That helps with every combination. Okay, what I'd like you guys to do, I've got some logic gates down here. And I would like you to draw the logic gates, write down the labels, write down the little notes underneath. So, or if anything is on, then the output is on. And I would like you to complete the truth tables for all of these logic gates based on what it's saying. And then what we'll do is we'll pause a bit, we'll come back, go over the answers, and fill in these truth tables. So first one's been done for you, which is an OR gate. If anything is on, then the output is on. There we go. So that's the OR gate. So next one, not, the opposite to the input. So if you've got on, which is a 0, the opposite will be 1. If you've got 1, then the opposite will be 0. Okay, so I hope you understand what I mean. Draw the logic gates down, fill in the truth tables, off you go. Okay, and guys, welcome back. And we did the first one, which is the OR gate. I hope you found it okay. So what I'd like to go through now is the AND gate. and this says if both inputs are on, the output is on. So both inputs, A and B, need to be on in order for it to be on. If it's not, then therefore it's off. So we've got off, off, so therefore it's 0. We've got off, on, so therefore they're both not on, so it's a 0. On, off, both not on, so therefore it's a 0. On, both on, so therefore it's on. Okay, we did the NOT gate together. It's basically the opposite. If it's a 0, it's a 1. If it's a 1, it's a 0. NAND, if both inputs are on, the output is off. So this is essentially completely the opposite to the AND gate. Now, this one, don't worry about it, it's not in our spec, but it's actually laid out like this. So how it's laid out is basically you've got an AND gate just here, like so. And what happens is on the end of this AND gate, you've got a NOT gate. That's what that circle represents. It represents a NOT. And it's referred to as a NAND. So for instance, here's your AND gate, and let's draw out a truth table. So we've got 0, 0 coming in. So if we've got a 0 and a 0 in an AND gate, a 0 will be output. So we've got a 0 just here because both need to be on. Then a 0 goes into this NOT gate, it becomes opposite, so a 1 is output. So let's try it with 0, 1. So we've now got, sorry, I haven't done my labels, A, B, Y. So we've got 0, 1. So 0 and 1, we have both need to be on in order to be on, so therefore it's a 0. And the opposite is a 1. This continues all the way until we've got both of them on. So looking at this then, we've got the 1, 1 to do. And so 1 goes in, so 0 comes out. Therefore, a 1 comes out. So in this truth table will be a 1. So these are the answers for the truth table on the NAND gate. Now the XOR, if A is on and B is off, the output is on. If A is off and B is on, the output is on. So basically, that is that. Everything else is off. XOR basically means exclusively OR. So they both can't be on at the same time and they both can't be off at the same time. It has to be either or. The next one is the NOR gate. Now, the NOR gate is like the NAND gate, but instead of a NOT gate on the end of an AND gate, it's a NOT gate on the end of an OR gate. So it's completely the opposite to the OR. So here's the OR. So we've got 1, 0, 0, 0. All right, and guys, so you guys need to know 3 of these as part of our course. So the 3 are is an OR gate, an AND gate, and a NOT gate. You need to know the truth tables for them, and you need to know the differences between the two and what they do at certain points. There could be many types of questions that come up. They may give you an equation and ask you to draw the logic gates for the circuit for it. They may give you a logic gate circuit and ask you to do a truth table for it. They may even give you a worded question and you have to do an equation for it or a circuit for it. Okay, so what we're going to be doing is we'll have a go at doing questions for each style, what the exam book could give us. So firstly is they give you a circuit and they say, well, what is the output of P? And then they could like give you some binary numbers for it. So let's draw out this circuit then. Okay, so this is a circuit and A is 1, B is 0, and P, we need to know what the output is. So if we've got 1 and 0 going to, this looks like an AND gate to me. So an AND gate, they both need to be on in order to be on. So therefore, they're not both on. So this is a 0. A 0 goes into NOT gate, which therefore P is 1. So they could ask you that, for example. They could ask you much more complicated ones, and you guys need to figure that out. They could even ask you to draw a truth table for this circuit. So the next question could be draw a truth table for the circuit. So in which you will say, right, you've got two inputs. So it's 0, 0, 1, 1, and 0, 1, 0, 1. And now we've got every single combination. We now need to figure out P for each one. So 0, 0 in AND gate is 0, opposite is 1, 1, 1, and you'll figure out that it's just literally the NAND gate here. Okay, so they could ask you to draw truth tables out. They could ask you a much more complicated circuit. So what I'd like to do is I'm going to draw a circuit and I would like you to tell me what the output will be. Okay, so here is my circuit. And what I'd like you to do, well, I've labeled them here because my drawings are absolutely terrible. I'm sure you guys can do a better job. So here we've got the input as 1, 0, 1, 1, 0, 0. Can you please tell me the output of P at the end when A is 1, B is 0, C is 1, D is 1, E is 1, 0, and F is 0. So pause the video, figure out that answer. What I find best here is to draw it out and just break it down to each individual separate gate. So for instance, I will start you off on this top one just here. So we've got 1 and 0 going into an AND gate. They both need to be on in order to be on. So therefore it's a 0 here. All right, so finish it off for me. Off you go. Okay, and guys, welcome back. So let's have a look at this AND gate down here now. So we've got 1 and 1 going in. Both need to be on in order to be on. So it's a 1. So now we've got in this OR gate a 1 and a 0. In an OR gate, anything needs to be on in order to be on. We've got this leg on here, so therefore it's going to be on. Right, this one, 0, 0 in an OR gate, so anything needs to be on. Here, nothing's on, so it's a 0. This 0 goes all the way up into this AND gate here. So we've got 1 and 0 in our AND gate, and both need to be on in order to be on. They're not, so it's a 0. Now into a NOT gate, it's the opposite. So 0 goes in, 1 comes out. And there we go. That is the answer. P here is 1. So you could get asked really like complicated questions, or like you could get given a big diagram. You guys need to be able to handle that at each point. It's not too bad. You just need to literally remember the 3 rules for each logic gate. Okay, the next style of question that you could have is you could be asked to basically draw out a logic gate, and they could give you like A and not B. So then you would have to draw out that diagram for it. So let's just write this down. A and not B. So here, what you do is just literally break it down. So the AND is between these two on this side here. So what's going to go in the middle here is an AND gate. Okay, so here it says A and not B. So A is just A, so we can just put an A leg in here. Now the next leg, on this side, it says not B. So let's do a not B. Not B. And that is the logic circuit for that question. So, okay, so let's try this one here. I'd like you to draw this one out for me. It says not A and not B. So pause video, draw it out, and then we'll come back and we'll go through it. Okay, so always look for the middle point, so the middle spot. We've got a circuit at this side, we've got a circuit this side. So therefore, in the middle is an AND, tying this all together. So let's put my AND in. Now it says, let's do the left side of the equation first. It says not A. So not A, that basically means the opposite of whatever A is. So let's put a NOT gate in. And now we've done the left side, so we can put A here. The right side says not B. So let's pop that in here. And then the output's just here. So there we go. We have not A and not B. All right, let's do one more. Okay, so now let's try this equation. It says A and B or B and C. So here, the glue in the middle is an OR gate. So let's firstly put in our OR gate. Okay, so we've put in an OR gate. Now what I'd like to do is I'd like to pause the video and fill in the rest of this for me. Okay, guys, welcome back. So what we do is we split the legs. So with the left side of the equation, we'll do first, it says A and B. So this is basically, here we need to break this down again. What's the glue in between A and B? It's an AND gate. So here we need to do an AND gate. And what we can do is we can just do an A leg, label it a B leg, label it B. And then this AND goes into this OR gate just here. There we go. So we've done the left side of the equation. Now we need to do the right side. It says B and C. Okay, so here in the middle of the equation, we've got an AND. So let's pop in an AND gate. Now, B, we already have a B leg. So when we've already got a B leg, or we need another wire coming off it, we put in a circle just here like this, and we just thread B into it as well. There we go. And then it says and C, so we need to put in a C leg. And then what happens is this threads in to our OR gate, and then the output is P. All right, guys, so that's complete. That is basically equation writing. We're going to advance on this a bit further throughout today's lesson. But what I'd like to show you now is just a bit of Boolean logic and how it's actually displayed. Okay, it's really crucial that you guys remember these symbols, because in the exam, they're not going to put A and B or not A and B. You need to remember the symbols because they're going to be drawing out, they're going to be putting the symbols in the exam to represent the words. So for instance, this little arrow here means and, the V is or, and then this backwards R means not. Can you please copy these down and right next to them and or not, because you guys are going to need to remember these. All I think of is the V is or, and then so that means the other way around is an and then the reverse R is not. So pause the videos and get these down. Okay, so I have a couple of questions for you now. So what I'd like you to do is I'd like you to write out the equation. So I will do the first one for you. It says AVB. Now we know that the V represents OR. So the first answer is A or B. What I'd like to do is I'd like to write out the rest of the questions. Okay, so pause the video, off you go. So the answer to question 2 is A and B, like so. The answer to question 3 is A or not B. Don't forget your brackets here, guys, because you don't want to be getting confused on which one's represented by not and stuff like that. The next one is not A and not B, just like that. And then we've got A or, and then we've got a bracket, not B and C, like so. We've got quite a few brackets in that one, just to basically show where the middle is. So it's quite obvious where the middle is now, because we've got brackets one side, we've got A the other side, so therefore the middle here is OR, which is clearly represented by that. Always look for that middle. The middle will help you out when actually drawing out these equations. Okay, so what I'd like you to do is I'd like you to now draw out these equations for me, and then we'll go through the answers. So the first one is A or B. So I'll help you out on the first one as per usual. Okay, so here we've got A or B. So the middle here is the OR. So let's do just a standard OR. Let's do the left side. So the left side is just an A leg. So A. And the right side is just a B leg. So B. Okay, so that's your answer for question 1. It's nice to have P equals, so then you can put a P on the end. Okay, so I'd like to answer the rest of the questions and then come back. Okay, and guys, welcome back. So the answer to question 2, which is A and B, is basically the middle is an AND gate. So let's draw an AND. And then we've got the left side of the equation, which is just an A leg. Then we've got the right side of the question, which is just a B leg. And then we've got our output just here. So that's the answer for question 2. Okay, so the answer to question 3 is, we've got in the middle just here an OR gate and a NOT gate. Well, that represents not B, so that's one side, and then we've got just A this side, so therefore the middle has to be an OR gate. So let's draw an OR gate. Okay, so now we've done our OR gate, but we've got to do the left side. Now the left side is just an A leg, and the right side is not B, so we need to do a not B leg. So not B. Good. Okay, so let's go to the go with the answer of number 4. Now again, we've got an AND gate in the middle, because yes, we've got a not this side, but the AND represents the two together. So we've got not B one side and not A the other side. So basically, all this is, guys, is just an AND gate with not A going in and not B going in. And that's the answer for number 4. Apologies about my diagrams, are not as good as yours will be. Okay, so the next one is, we've got a equation in the middle, which is just an OR gate here. So let's draw our OR gate. Then we've got our left side is just an A, so let's pop in an A. Then our right side of the equation, we've got not B and C. So here we're going to need an AND gate for the right side. So let's put an AND gate in. And going into this AND gate is not B. And here we've just got a C leg. And then this flows through to our OR gate, which is the right side of the equation. All right, and guys, I hope that helped. I hope that makes sense. These equations can get quite complicated at times. So you just need to break them down, find the middle, and then just keep on finding the middle, and you'll get there with drawing them out over time. Okay, so the final part is that the exam board could ask you what the equation is. They'll give you something simple to see what the equation is. Tricky is just work back. So here we've got P, and we've got a NOT gate, and then this NOT gate, we've got an AND gate. So here, working back, we've got NOT in our AND gate, A and B. So here, if I was writing this out in English, it would look like this. However, what we need to do is we need to put it into Boolean logic, so it will look like this. Hope that makes sense. All right, I'm going to draw a logic circuit out, and I'd like you to tell me what it is. Okay, so on the first question as well, I should have put P equals, because we've got output P here, so it's P equals, not A and B. All right, so this next one, please. Can you please write what the equation would be for this one in English and then in Boolean logic for me? So pause the video, have a think, and then come back. All right, guys, welcome back. I hope that was okay for you. So here, working back, we've got P equals, we've got a NOT gate just here, so NOT. And then we have A and B, but we've got an OR gate here. So this is not A or B. Ta-da! Just like that. All right, so I'm going to do one more final one. Okay, then, guys, so this is the third and final question. I've labeled this an OR gate here because it's just very terrible drawing. I apologize. I hope yours are better. So can you please figure out the equation, and then come back? All right, guys, I hope you found that okay. So let's go over the answers. So let's work back. We've got an OR gate just here. So we have an OR gate. So let's write OR. So P equals. So we've got a C going into this OR gate. So C. And then on the left side of the equation, we've got an AND gate. So A and B. So OR is the glue that's tying these together. So in the middle somewhere, we're going to have OR. And we're going to have a C here because it's just a C leg. On the left side of the equation, we've got A and B. So it's going to be A and B. And let's put some brackets in so it's nice and simple. And there we go. Now let's convert it to Boolean logic. So we've got P equals A and B or C. All right, guys, so that is it for today. I hope that was okay and that you understood it. By all means, please do watch the videos. Again, there's lots of YouTube videos out there as well that helps with these logic gates. If you're unsure, by all means, please do drop me an email. I'm more than happy to help. Okay, so that's the end of the lesson. I'll see you next week. Thank you. Bye-bye.